Okay, so yesterday I talked about modeling of physical systems. So let me just quickly go over what we discussed yesterday. And I told you that to model mechanical systems, we use certain elements, and there are basically three main types of elements. These are the inertial elements, and then we use springs and dampers. And for a lot of different type of mechanical systems can be modeled by just using three main elements. So we're going to see some examples of that later on. And basically, if you have an inertial element, that adds dynamics to your system, because for masses and inertias, we need to write Newton's second law of motion, which is a differential equation. So we have dynamics in the system whenever we have an inertial element. And for springs, we use this equation for a linear spring, and this is just a static element because there is no differentiation involved. And then there are dampers. Dampers are also dynamic elements because they have this equation. And just like spring, if B is a constant number, then your damper is a linear damper. But in case it changes with system variables, like if this is a function of y or y dot, then that means your damper is a nonlinear element. So we just solved this simple example where there was a mass connected through a spring and a damper. So it's a very simple mechanical system, but it's a very useful system because it contains all the elements used in modeling mechanical systems. And then we talked about degree of freedom. So degree of freedom is an important concept, and it basically tells how complex your system is. If you, for a 1 degree of freedom system, you know that there is motion in just one axis, and it is very easy to study. Every time a new degree of freedom is introduced to the system, you need to consider more differential equations, and your system will become more and more complex. And then this was the example I was doing yesterday, but I didn't really have the chance to finish it. So I'm going to start from here. So we're making a simplified model for a car suspension system. It is simplified because we're ignoring certain dynamics. If you consider a car, it has 4 tires, right? And each tire will have independent motion, so it has a lot of degree of freedom in there. So the simplification we're making here is we're taking just one wheel and thinking of it as independent of the remaining wheels. So we're just studying the dynamics of a single wheel. And then we assume that there's just motion in the vertical axis, so we ignore any other motion in any other dimensions. So that means the mass of the car can only move up and down, so there's 1 degree of freedom here. And then we also consider the mass of the wheel, so it also can move only in the vertical axis. So there are 2 masses with 1 degree of freedom each, which makes the problem 2 degrees of freedom. Okay, so yesterday I thought I couldn't really explain really well why we ignore the gravity. So let me try to do it one more time. Normally, since these are in the vertical plane, we should also consider the weight of these masses, right? The car obviously has a mass, the wheel has a mass, and there's the weight force acting on these. But we can just simply ignore them, and this doesn't really change anything. And let me tell you why. Okay, so normally consider that there was no gravity, and the springs, both the spring here and spring here, will have some neutral length, right? But when you put the car on with gravity, with the weight of the car and the wheel, the spring will get compressed, right? When everything is at rest, the car is not moving. Due to the weight of this car here and the wheel, these springs will be compressed by a certain amount. Okay? There will be some delta deflection of these springs, and the amount of these deflections will be such that the spring force will be balancing the weight of the car. So there will be an equilibrium. So when there is motion, when the car is moving and it gets some disturbances from the road, the spring deflection will be changing, but this equilibrium terms will always be there. So in other words, the gravity will always be there, and this delta deflection will always be there. So what I'm saying is, we can cancel these terms and assume that the deflections are taken from with respect to this condition where the gravity was in effect and the car was in equilibrium. So in other words, normally there's a delta deflection here and a gravity on top of that, which cancel each other out. And when we come here, I ignore the delta deflection of the spring and the gravity force at the same time. Okay? So I ignore a collection of terms, but the sum of these terms are equal to 0 anyway. Okay, so if I do that, the delta deflection of the spring is gone, and I'm measuring the deflections of the springs from by taking this as the reference point, and the gravity, the weight forces are ignored. So anyway, to write the equations, I make this assumption. So I say that Ys, Yw, and Yr, they are all positive, and they follow this inequality. Ys is the greatest one, Yw is the second greatest, and Yr is the third one, which means all the springs are in extension. Okay, so Ys is the amount this has moved upwards, the car body, and Yw is the amount the wheel has moved upwards. But since Ys is greater, the spring here is in extension. Okay, and similarly the spring here is in extension as well. Also, that's the important thing, because that knowing which way the springs are deflected will allow me to write the directions of the spring forces correctly. Okay, so after that, it is really very easy to write these forces. So I write the spring force and the damper force. Similarly, with the help of this assumption, I can write the direction of the damper force directly. So the two forces are in this direction for the car mass. For the wheel mass, there are four forces. Two forces are coming from the spring and damper above the wheel, and the other two forces are coming from the spring and damper connected here, and they have these expressions. Okay, so now I have written all the forces acting on all the masses. So from that point on, I can just write the differential equations directly. Okay. So let me show you what the equations look like. So these are the final equations. So this is the same problem. I just drew it. I found this in my computer, so I thought I should show this. And there are some numerical values. In the future, we can use the numerical values to simulate this car problem. But right now, all we care about is these equations. Okay. So I wrote the Newton signal of motion one time for the car mass, which is this equation, and then I wrote the same equation one more time for this mass, and that gives me this second equation. So in the end, I have two equations, two second order differential equations. Okay, and since we assumed all these terms to be constant numbers, the equations we get are linear differential equations. So we have a linear dynamic and time invariant system. Okay? Do you have any questions so far? So let me talk about these equations a little bit. Okay, so first of all, so what do you think is the input to this system? In other words, what will make the system move? So we have Ys here. So this is one of the outputs, right? This can be taken as the output position of the car. This is not an input, obviously. We have Yw. This is the position of the wheel. That's also a possible output. So the input to this system is this Yr here. So there is what can possibly make the system move. So if this car is driving and the road is perfectly horizontal, then the car will remain in an equilibrium condition, right? Nothing will move. But if the car is driving along a rough road surface, as you see here, then the road surface variations will cause the car to move. So in other words, this is an input to our system, and if we are driving through a rough road surface, then due to these YR variations, this spring force will be changing, and that spring will cause the wheel to move, and as the wheel moves up and down, the car itself will start moving. So the passengers will be feeling that changes or variations on the road surface. Okay, but YR is not something we can change, right? So that's not a control input, but it is rather a disturbance input. Okay, so that's one thing I would like to say here. So there are many systems in real world like this without any control input. So it is a system, but we don't have a direct control over it. There may be a disturbance, and all we can do here is to try to reduce the effect of the disturbance. So anyway, okay, so that's the first thing. The other thing is, look at these two differential equations. So this is a second order differential equation on ys, because the highest order derivative is the second derivative of ys. But we also see yw here, okay? And then if you look at the second equation, this is a differential equation with the highest term being yw double dot. But we also have ys here. That means these two equations are connected, so we call them coupled. So that means we cannot solve these equations independently. It's not like you solve this equation first and then you solve the second equation. You have to solve these two equations at the same time, simultaneously. Because the motion of these two masses are connected. So when one of them moves, the other one gets affected by the motion of the first one. And that means we have a coupled system, and the equations need to be solved simultaneously. Okay, so for system analysis, what we need to do is we need to solve these differential equations. And when we do that, we can answer questions like, what happens if the car drives over a certain road surface? In fact, this was asked before and as an homework. So I can give you a road surface. I can define this YR function. It can be a sine wave, or it can be a square wave. It can have any random shape. And you can find, for example, how the ys will move when the car goes through that disturbance. Okay? So obviously you don't want ys to be affected by YR too much, right? So that means the car is not comfortable. In fact, ideally you would like ys to remain constant no matter what YR is. That would mean the car, you don't feel anything while driving over rough surface. So what you can do to improve that is you can choose these parameters. So you can choose an appropriate spring constant or an appropriate damping constant to improve that performance. Or now in some cars they do some active control. They can change these things. They can change spring constant and the damper constant mechanically to make this car more comfortable. Okay. So anyway, I think it's enough about this example. Let's move on to our next type of systems, which is electrical systems. I will show you more examples of this, but first let me show you the electrical systems. Oh, by the way, this is the lecture notes file you have, but it is not very clear, right? In certain parts, it's not easy to read what is written there. So I found another set of notes, and this is better. So let me give you this one as well. The contents are exactly the same. It's just these were written by another student, and it is somehow more clear. So let me give you this file as well. So anyway, let's come to these electrical systems. So very much like the mechanical systems, to model electrical systems, we use a certain number of elements, and these elements are the following. The first element is a resistor. It's used to control flow of electricity in a circuit. So this is the symbol we use to represent a resistor. It's pretty much like the same symbol as the spring. If you apply a potential to the two ends of a resistor, V being the potential difference, then there will be a current flowing through this resistor, and it is given by this relation. Okay, so this is the equation for a resistor. And similar to a spring, the resistor is also a static element, since there is no differential equation here. The next element is a capacitor. The capacitor is shown with this symbol, and physically a capacitor is composed of two conductive plates with a non-conductive material between them. And capacitors are used to accumulate electrical charge. To study the behavior of a capacitor, these equations are used. Each capacitor has a capacitance represented by capital letter C, and that capacitance is defined as the following. It is the amount of charge stored per voltage difference applied. So this V is the voltage between the terminals of a capacitor. Q is the amount of charge stored inside, and this relation gives the capacitance. And the current flowing through a capacitor is given by these differential equations. Current is equal to the rate of change of the charge stored within the capacitor, and by using this relation, this current equation can be written as C times dV by dt, where V is the voltage. Okay, and as you can see, there's a derivative term here, which means a capacitor is a dynamic element. So whenever there's a capacitor in a circuit, then that circuit is a dynamic circuit. Okay, the third element is an inductor. For inductor, we use this symbol, and if you assume that there is a potential difference of V between the terminals of an inductor, the relation between the potential applied and the current flowing is given by this differential equation. By the way, if we move up here, if R is a constant number, then the resistor is a linear resistor. In the case of a capacitor, if C is a constant number, it is also a linear capacitor. And for inductor, the inductance L, if that's a constant number, it is a linear inductor. Okay, so in case they change with some certain system parameters, then that variation will make these elements nonlinear elements. Okay, but for our purposes, we will always assume that these are all constant numbers, so you don't need to worry about these numbers being variables. And then finally, you need a voltage source. The voltage source can be either a power supply, in which case we use this symbol, or it can be a battery, and for batteries these symbols are used, as you remember from your physics courses. And these basically create a voltage supply, right? So okay, so you can use an electrical system by using a combination of these elements, and these are how you use these elements to obtain the equations for an electrical system. So you can use the Ohm's law, which is basically the equation for a resistor we saw before. And if you have resistors connected in series or parallel, you can use these relations. So for serially connected resistors, you simply add the resistances. But if you have a parallel connection, then you can find the equivalent resistance using this relation. Then there are two Kirchhoff laws, and those are the laws that allow you to write the overall equations. The first one is says that the sum of currents entering and leaving a node is zero. Okay, suppose that you have a connection point and several wires are connected into that connection point, and this law says that whatever current flows into the node should be equal to the current leaving the node. Okay, so you simply add the entering and leaving currents, and the sum should be 0. And the second part of the Kirchhoff's law says that if there's an electrical loop, the algebraic sum of voltages around any loop is 0. So you write the potential differences. There's a voltage source and there's a current flowing resistor. There will be a potential drop here, and then another resistor, another voltage drop, and then when you come back to the starting point, you should end up with 0. Okay, so you add all these potential differences and the sum should be 0 around any loop. Okay, and you must have done this in your physics courses, right? In Physics 106 and even at high school, I remember doing things like this. Okay, so let's take a look at this example. We connect an inductor and a resistor through a battery like this. So we basically write the Kirchhoff law around the loop. We start from here. There's a battery, and here you need to be careful about the signs of the voltage changes. Okay, so this is a voltage source. It has a positive voltage, and then the current is flowing through an inductor and a resistor, which will cause voltage drops. So you add the voltage terms for the inductor and the resistor as negative, and then this becomes the equation for this system. Okay, so to consider this as a system, the input is the voltage applied, and for output you can choose the current flowing through the circuit as your output. And the relation between them is given by this equation. And this is a differential equation because there was this inductor, which is a dynamic element. So by the way, here let me just remind you that the inputs of a system are given, they are fixed. But for outputs, you can choose different things as your output. So output is not unique. So I think I can explain this better on the previous example. So let me come back to this. So here there was just one input, which is the road surface coordinate here, yr. But for output, I have different options. For example, I can choose the position of the car as my output, which is ys coordinate. Okay, I can also choose yw, the position of the wheel, if that is what I want to look at. Or I can choose, for example, the relative distance between the car and the wheel, which is ys minus yw. That's also valid output. Okay, so if I'm interested in how much the wheel gets close to the car, if that's what I want to look at, I can choose that as my output. So output is not unique. For the same system, you can define different outputs. Okay, so in real world, as aerospace engineers, pretty much all our systems contain combination of these different types of systems. So there's some electrical part and there are some mechanical parts, and they work together. And a very good example of that is an electrical motor. So let's take a look at how we can model a DC motor. Okay, so this is a very, very important part, and for any mechanical system, we use motors to create motion. Okay, so if you are designing an unmanned air vehicle, for example, you use electric motors to control the control surface deflections. For elevators and ailerons, you use such electric motors. Or most such small vehicles are propelled by propellers, so you use an electric motor to run the propeller. Or for robotics, for example, if you are designing a robotic arm, you use such electrical motors to control the motion of the robot. So we use these parts everywhere. Okay, so I don't know if you ever played with an electric motor, but a simple electric motor looks like this. So I used to play with motors a lot when I was a kid. So I don't know if you are all like that, but if you take apart a little electric motor, inside there are some magnets around the motor, and inside this is the part that rotates, and there's a huge amount of wire wound around some windings. So these are all electrical wire, and there are some terminals here. This is the part where you apply voltage and it starts rotating. Okay, so this is the inner workings of a brushed DC motor. So this is the part where we applied voltage, right? So you apply voltage and it somehow starts rotating. In reality, we have this long wire wound around these windings. So we model that using a resistor and an inductor. Okay, so the resistor represents the resistance of all these wires inside, and since they are wound, it acts like an inductor. So to model that inductance, we use an inductor element in the circuit, and when you apply voltage, there will be a current flowing this circuit, and that current somehow creates a torque and motion. So this represents the actual rotating part, this part, and you get a torque here, and that torque causes the motor to rotate. And when the motor is rotating, there is a potential difference which is called the back EMF voltage. So there is a potential change across this rotor. So that is called VB here. So these are the elements, basic elements in the circuit. So we write the Kirchhoff's law. This is the voltage source, and then the voltage drops due to the resistor and the inductor are written by these two terms. So this is the same element as the previous example. We just have one additional term, and this additional term is due to the voltage drop of the rotor rotating, the back EMF voltage. So this is the equation for an electrical motor. So this is the current flowing. R and L are constant numbers, and there's just VB term which we don't know yet. This back EMF voltage depends on how fast the motor is rotating, and we use this linear relation for that. So the back EMF voltage is equal to the rotational speed of the motor times a constant number. That means if the motor is rotating very fast, then there should be a large back EMF voltage. But if it's rotating very slowly, then this is going to be a small number. And if it doesn't rotate at all, then the back EMF voltage will be 0. Okay, so this is the simplified equation we use for the back EMF voltage. So here's how a motor works. You connect the voltage, and the voltage you apply creates a current which can be calculated by solving this differential equation, and that the current creates a torque. The mechanical torque you get is proportional to the current flowing. So this is the last piece of the equation. When you find the current, the torque you get is proportional to the current. Okay, so these are all linear equations if you look at them. So we have current here, and it's just a current by itself, so there's no nonlinear function, and then there are no cross multiplied terms like current multiplied with the angular speed or any other such nonlinearities appearing in these equations. So everything is, as long as all these numbers are constant numbers, everything is linear in this set of equations. So with these assumptions, the motor becomes a linear system. Okay, and the input to the system is the voltage. Okay, this is what drives the system. This is what creates motion. So this is the input. And since we can change it if you want to, we consider this as a control input. And the output, the natural output is the torque output of the motor. But again, the output is depends on our needs. So if you want to control or look at the amount of current flowing, you can define the current as the output of the system. Okay, so this is how we model an electric motor. Okay, so if you think about this back EMF voltage, it depends on the rotational speed, right? If the motor is turning fast, then you get this VB a large term since it is proportional with the rotational speed. So this property allows a motor to be used as an electrical generator. So suppose that there's no voltage source. Okay, suppose the V is equal to 0. You didn't connect any voltage, and somehow you get motion here, right? Somehow the motor starts turning, which creates an omega. This is the rotational speed of the motor, and that will give you some voltage. This back EMF voltage now will be appearing here. You didn't have any voltage source at all, but if you just rotate the motor, you get voltage, and this means that you can use this as a generator. So any electric motor, if you turn it, that becomes a voltage source, voltage generator. So in this case, the input and output becomes reversed, right? The input becomes the torque, so you apply torque externally, and that gives you voltage. And this external torque source can be coming from wind, water flow, etc. So in any wind turbine or hydroelectric turbines, you use the same concept in the opposite direction. Okay? So how are we doing so far? Okay, so we have about 10 minutes, and there are a few examples I would like to show. So I guess we can start talking about this. So this just puts what we have seen before, and it represents a very real system that we use in a lot of different places. So this is an electromechanical servo system to regulate the deflection of a control surface. Okay, so this is obviously a simplified version. In real system, there are like some mechanical connections here, gearbox, and there are some mechanical linkages. But here I just remove everything, and I just assume that the motor is directly connected to a control surface. So that means if you rotate the motor here by applying voltage, that will directly change the control surface deflection. Okay. So if I define the angle here as theta, the speed of theta, which is d theta over dt, will be the omega, and this is the same omega that we should use in these equations, right? Like this omega is equal to that omega. And again, in a real system, there's going to be a gearbox here, which will scale these quantities. But just for the sake of studying this example, we can ignore all of those details. So in a real setup, there will be this gear ratio. The omega to be used in this equation, in the back EMF equation, it will be different than this d theta over dt by some gear ratio. But you don't need to worry about that right now. Okay, so let's take a look at the elements in this system. So we have a voltage source, a resistor, and an inductor. These are to model the windings of the electric motor. And then there will be, the output will be a torque. The torque will be applied to this control surface, and then it will cause the control surface to rotate. Okay, so there's a mechanical part which can rotate. That means there should be a moment of inertia for that part. So there's a mechanical inertial element here, right? So we need to write a second order differential equation for this part, and then we need to write the equations for this electrical part. So you see those equations written next. The equation for the electrical part is the same as what we had before, and so this is the equation for the electric motor, and then there's this omega term. For the mechanical part, we have this differential equation. The total moments acting on that control surface will be equal to the moment of inertia of the control surface times its angular acceleration. So this is the second equation. And just like the previous car suspension problem, we have two equations, but these equations are connected. In this equation, you have the motor torque, Tm, which is connected to the circuit current, and this current comes from the first equation. And in the first equation, there is omega term, but omega is equal to d theta over dt with this gear ratio, and that d theta over dt comes from the second equation. Okay, so the angle, the rotation of the control surface is found by the second equation. So for this, control servo, we have again two equations, and these two equations are connected through the angular speed and the electrical current. Okay, so again we have two equations, and these two equations need to be solved simultaneously to see how the system works. Okay? Do you have any questions? So you can make this by using these elements. You can model complex systems. For example, let me give you some ideas. And in fact, I'm planning to make these ideas homework problems for you, or I can ask these in the exams. So we can take this same setup here. And I can connect this to like a vertical pendulum, for example, right? Or inverted pendulum. So this is a very nice problem, right? We solved the equations for a pendulum before, and then we connect it to a motor. So this way we can obtain the equations for this problem where we have this inverted pendulum, and we can apply a torque here. So this is the torque created by the electric motor. So let me call it TC. And then I can ask you to study this system. So first you need to write the equations, and then I will ask you, once we learn how to solve these equations, I can ask you what happens if you give a certain voltage, how the system will move. Or to make the system more interesting, we can add a second link here. So it becomes a double inverted pendulum. see. So this was a very interesting problem. So this was asked in homework 2 years ago. This again shows a connection of an electrical system with a mechanical system. I want to show you how to write the equation for this system. There are certain tricks that you need to see. But I don't want to start this since we have very little time. So let me show you the problem first, and then we can talk about this next week. So we have the same electric motor as before, and then we get the torque. But this time, torque is used to move a cart back and forth, and this drives this spring mass system, spring mass damper system here. Okay, so we will talk about this system next week, and I guess we can just stop here for today.